is essentially gas stoichiometry. So let's just look at a problem, okay? Let's say we have CH4 gas plus O2 gas. We're going to do a simple combustion problem. Yields CO2 gas and H2O gas. Okay. And I told you that this was run at 300 degrees Kelvin. I don't know. And you start with 2.6 grams of CH4, and you want to figure out how much CO2 there is. Okay, grams. So take a second or two. I'm going to fill up my water. Take a second or two and see if you can figure out that problem. All right, so if we look at this problem, we've done these before. Okay. Well, I have 2.6 grams of methane, I got to get to moles, so the molar mass is 16 for methane. And then I got to use my mole ratio, which means I got to make sure I'm balanced. All right, so I need a 2 there and a 2 here. All right, but I'm balanced now. Okay, so 1 mole of methane gives me 1 mole of CO2. And then 1 mole of CO2 has 44 grams of CO2. And we would do it that way. We've been doing it since chapter 3 that way. But here's my issue. These are gases. I can't weigh a gas. What am I supposed to do? Use a beaker, catch the gas, and run it over to the balance? We already know that beakers aren't really empty. They're filled with air. So what am I really measuring? So doing it this way, even though we did problems this way, isn't really the correct way. What I would need to know is, well, not only are we at 300 Kelvin, but we might be in a 1,000 mil container at 1 atm of pressure. And if I want to figure things out, like how much CO2, I wouldn't ask how many grams of CO2. I would ask how many liters of CO2 am I getting out? Well, how am I supposed to do that? Well, you do the same method. You start with 2.6 grams of methane. We figure out how many moles of methane we have. 16 grams of methane, 1 mole of methane. We look at our mole ratio. 1 mole of CH4 gives me 1 mole of CO2. But here's where we stop. We do the math and we figure out how many moles of CO2 we have. 2.6 divided by 16 is 0.1625. I should have realized that. Okay. 0.1625 moles of CO2. But we didn't ask for moles, we asked for liters. And that's where all of this information comes into play. Let's say they didn't tell us the volume. Because, again, we're going to expand to find the volume. What if they gave us the temperature? They gave us the pressure. We have the number of moles now, and I want to know what is the volume. Well, my volume would equal nRT over P. I know what N is because I calculated it. I know what R is because that never changes. I know what T is. They told us 300 Kelvin. And I know the pressure. They told me 1 atmosphere. So we take the 0.1625, multiply it by 0.0821, multiply it by 300, and we get, hey, we have 3.99 moles of CO2 we would have created using this problem. Okay? So let's take a look at another one right out of the slides here. It says, what is the volume of CO2 produced at 37 degrees Celsius in 1 atm when 5.60 grams of glucose are used up in the following reaction? Now, this is glucose right here. C6H12O6 is glucose. All right, glucose plus 6 oxygens gives us CO2 and water. Okay. They tell us the temperature, they tell us the pressure, and they give us the grams of glucose. So our steps. Number 1, convert the grams of glucose to moles of glucose. Step 2, convert the moles of glucose. So this one, you're going to use the molar mass. So let's see. Let's see how well I can write with the pen today. Here you're going to use the... Not too well, Jay. Not too well, buddy. Here you're going to use the molar mass of glucose. All right? Then we're going to take our moles of glucose and get it to moles of CO2 using our ratio. It actually doesn't look so bad. Okay. Then we're going to take the moles of CO2 and use PV equals nRT to find the volume. And we're going to manipulate it to be V equals nRT over P. Now, we have to notice a couple things. 37 degrees Celsius. I need to get that to Kelvin. ATMs are fine. And the N comes from this right here. Okay? Questions? So let's do the problem. Convert it to moles using the molar mass. Use the mole ratio, 6 to 1. Okay, 6 to 1. Find the moles of CO2. Found the moles of CO2. Now plug it into PV equals nRT. Guys, it's nothing new from what you've been doing. Okay? I can't stress that enough. It's nothing new from what you've been doing. It's using grams, converting it to moles, converting moles to moles, using mole ratios. You've been doing it. The only thing we are doing different is that we are adding the PV equals nRT stuff that we learned. Okay? Questions on stoichiometry and using the gases for stoichiometry. So the moles you find of the gas gets plugged into PV equals nRT to find the volume. That's what really it sums up to be. Sorry, I put moles down here before. This should have been liters. My bad. Just caught my mistake. Liters. Okay. Because we're solving for volume there. Questions, questions, questions. Because we have one more thing left for this chapter, and that's it. Yes, which has absolutely nothing to do with gas laws, but yes. Yes, theoretically, that's what you should end up with in the lab. All right, so there's one more thing to... But you need to show all the math to get there. I say that in the video. One more thing. Dalton's law of partial pressures. Very simple to understand. I have a container. Inside the container is A gas and B gas. A gas is exerting a pressure of 2 atms. B gas is exerting a pressure of 1 atm. Dalton's law of partial pressures basically says that the total pressure inside the container is 3 atms. And the deal is the gases will act independently, like they're the only gas in there, doing their thing. Dalton's law of partial pressure says pressure total of a system is equal to P1 plus P2 plus P3 ... Okay. So, if I told you that 80% of our system is A gas and 20% is B gas, and the total pressure inside the container is 10 atms total, and I want you to find the pressure of each gas, well then the pressure of each gas would be 8 atms for A and 2 atms for B. Yeah, that's the whole idea of the lab, Kelsey. It's to try to start with the same amount of copper. But you need to show all the math. See, I did it a little different for my guys. And I'll talk about that as soon as I'm done with this. Now, what if this said, I wanted to know, let's try this. Okay, and I want to point this out since they're interchangeable. And the way Dalton figured this out was he basically said that humid air is dry air plus water vapor. If I take the water vapor out, I still have the same pressure of dry air. It's just that the water pressure or water vapor adds pressure to the system. So what if I said to you this? What is the pressure of A, okay, and the pressure of B in this situation if I have 10, let's do it this way. I have 5 moles of gas, all right, 5 moles total. Well, I could do this 2 ways. I could take 80% of 5. Okay, so there's 2 ways to do this. Take 80% of 5 and find the moles of A. Take 20% and find the moles of B. And then plug them into PV equals nRT. Or you could do it this way. Do P equals nRT over V. Be given a situation, say that this is a 200 milliliter flask. And it's at 100 Kelvin. So I could do pressure equals 5 moles times R, 0.0821, times the temperature, 100, over 0.2. Find the total pressure. Okay. So my total pressure will be 500 times 0.0821 equals that divided by 0.2. I get 20.5. total ATMs. And I can figure out A and B by taking 80% of 20 point. Clear this. $20.5 times 80%, 0.8 is 16.4. And then 4.1 would be B. I could do it that way. Okay. So all I did was take this times 80%, or times 0.8. Okay, and got the 16.4. Or the other way to do it, take the percentage of the moles originally and solve for the pressure over here. So there's two ways to do it. Okay. The key that I find that people get mistakes on the exam all the time is if I gave you something like 0.2%, people forget to convert that by dividing by 100. But that's all Dalton's law of partial pressures is stating. And that's essentially the end of the chapter. I mean, you could look through all the PowerPoint slides that go into, you know, lots of thought and looking at it, and not thought, but a lot of explanations. We aren't going to do gas over water just because of time constraints. So for homework, let me see here. Stoichiometry. Page 250. 5.53 to 5.56. Slide number 58. Okay, which is sample problem 5.9 that deals with Dalton's laws of partial pressures. .96 on page 252. 5.96. Okay. All right. Now, with lab, guys that have me for lab, I posted a video online, and I posted the lab assignment up on Blackboard last night. The idea is you got to go through all 5 reactions of the copper reaction, taking your initial 0.5 grams of copper and converting it to the different copper components that you're going to make during the reaction process. Okay? That being said, I want you to find the grams of each product. As Kelsey was saying in the chat here, this was a percent recovery lab you would have done. You were trying to get as close to the 0.5 as possible. So if everything works out perfectly and you do all the math perfectly, the 0.5 grams of copper you start with, by the time you get to the end, should be 0.5 grams of copper again. Now, I also gave a experimental value for you to do your percent recovery, aka percent yield, and a percent error. I think I gave you like 0.4 and change of what you really recovered in lab. I wanted to see you convert that 0.5 grams of copper to each product and tell me how many grams of each product you should have gotten along the way. So the lab is up on Blackboard under the assignments. The amounts and what I'm looking for is up there, and there's a video on Blackboard to help you through the calculations. If those don't help you, then feel free to email me. Okay?